All right, today we're going to pull back the curtain on the elegant three-step dance that happens under the hood every single time you run a command. It's a process so fundamental, it is literally at the heart of how our computers work.
I mean, think about it. You've probably done this 1,000 times. You type ls, you hit enter, and bam, the results just appear. It feels like magic, right? Well, it's not magic. It's a carefully choreographed sequence of events. And by the end of this, you'll understand exactly how that trick is done.
So here's our game plan. First, we'll talk about the two separate worlds inside your computer, user and kernel. Then we'll look at the bridge that connects them, which are called system calls. After that, we'll meet the stars of our show, fork and exec, see how they work together in the classic fork-exec wait pattern, and finally, we'll learn why we have to clean up properly to avoid these creepy things called zombie processes.
Okay, so before we can even talk about creating a program, we need to understand a really core concept of how operating systems are designed, this idea of a separation of powers.
Think of your computer as having two distinct modes. First, there's user mode. This is where all your normal applications live, your web browser, your code editor, the terminal itself. For safety, these programs have very limited privileges. They can't just go and mess with the hardware directly. Then you've got kernel mode. This is basically God mode. The kernel has full, unrestricted access to everything, the CPU, memory, your hard drive, all of it. This separation is a super important security feature that keeps a badly behaved app from crashing your entire system.
So if your program is stuck in this safe little user mode sandbox, how does it do anything useful? How does it create a new file or send data over the network or, create a new process? Well, it needs a safe and controlled way to ask the all-powerful kernel for help. And that bridge, that's the system call.
You can think of a system call as the official API for the kernel. It's the one secure front door that an application can use to knock and say, "Hey kernel, I'm just a humble user program, but I really need you to do this privileged thing for me." It's this controlled process that lets our computers be both incredibly powerful and remarkably stable. So let's break down how this works. First, your program calls what looks like a totally normal function, but under the hood, this function triggers a special instruction called a trap. It's like ringing the kernel's doorbell. Instantly, the CPU switches from user mode to kernel mode. The kernel takes over, checks if the request is valid, and then does the heavy lifting. Once it's done, it puts the result in a special spot, a register, and switches the CPU right back to user mode. Your program just continues on its way, usually with no idea that this whole powerful context switch just happened. All right, so we know how to knock on the kernel's door. Now let's make our first real request to create a brand new process. The system call for this is one of the most famous ones out there, and it's called fork. Okay, the fork system call is beautifully simple, but also a little bit mind-bending. When a process calls fork, the kernel literally creates a near-perfect clone of it. It's like hitting a copy-paste button on an entire running program. The original is called the parent, and the new copy is called the child. For a brief moment, they are identical, running the exact same code from the exact same spot. So this is where it gets really clever. We have two identical processes running the same code. How on earth do they know which one is the parent and which is the new kid on the block? The magic is all in the return value from fork. The parent process gets back a positive number. That's the process ID of its new child. But in the child process, fork returns 0. And that difference is everything. It's a signal that lets the brand new clone realize, aha, my return value is 0. I'm the child. My job is to go do something different. Okay, cloning is cool and all, but it's not super useful if our goal is to run a different program, like ls. We don't want another copy of our shell, right? We need to completely transform this new child process into something else, and that is the job of exec. The exec system call is a total identity swap. It's like a complete brain transplant for a process. It takes the process that calls it and just completely overwrites its memory. All the code, all the variables, the whole shebang, with a brand new program that it loads from the hard drive. The process ID stays the same, but its personality, its mission in life is completely new. And this is so important to get right. Let me say it again. Fork creates a new process. Exec replaces an existing one. Exec is what hijacks that child process we just created and gives it its new purpose. And here's a fun fact. If exec succeeds, it never returns control to the original code because that code doesn't exist anymore. It's been completely wiped out. So now we can put it all together.
This combination of fork and exec is the fundamental pattern for how your computer runs pretty much everything. And you might be asking yourself, why the 2 steps? Why not just one system call that creates and runs a new program? Well, that's a great question, and the answer is all about flexibility. That tiny little gap, that moment in time between when fork returns and when the child calls exec, is a golden window of opportunity. The parent can use that time to set up the child's environment, like redirecting its input and output before the child transforms. That simple separation is what makes powerful shell features like pipes and redirection possible.
So here is the entire dance, step by step. Number 1, the shell calls fork, cloning itself. Number 2, in the new child process, the PID is 0, so it enters that if block. Number 3, inside the block, the child immediately calls exec, transforming itself into the LS program. And finally, number 4, back in the parent, which received the child's real PID, it calls wait, which basically tells it to just pause and chill out until its child, which is now the LS program, is completely finished with its job.
Now, that wait call, it's not just about the parent taking a coffee break. It serves another incredibly important purpose. It's all about being a responsible parent and cleaning up after your kids. So, what happens if the parent is irresponsible? What if it just forks off a child and then moves on with its life without ever looking back or calling wait? Well, this leads to a pretty spooky phenomenon in the operating system world.
You get a zombie process. A zombie is a process that's already finished its work. It's dead, but its entry is still lingering in the kernel's big list of all processes. Why? Because its parent hasn't officially acknowledged its death by calling wait. So it's not running, it's not using CPU, but its ghost is still occupying a slot in the process table, which is a finite system resource.
Now, don't get zombies confused with orphans. They're different. An orphan is a process whose parent died before it did. The operating system actually has a really neat plan for this. A special process, usually the very first one called init, acts like a system-wide foster parent. It adopts any and all orphan processes and makes sure to wait for them so they can terminate cleanly and don't become zombies. And this brings us right back to wait. It is the parent's fundamental duty. It does 2 crucial things. 1, it pauses the parent until the child is done. And 2, and this is the important part, it reaps the child. That's the technical term. It tells the kernel, okay, I've seen that my child is done. You can now wipe its entry from the process table. It's the final act that prevents a finished process from becoming a zombie. This right here, this is the money shot. If you only remember one thing from this entire explainer, make it this sentence. Let's say it together. Fork creates, exec replaces, and wait cleans up. That is the fundamental life cycle of nearly every command you have ever run on your computer.
So we've cracked the code for how a single command runs, but let's take it one step further. How do you think a shell handles a command pipeline, like piping the output of one command directly into the input of another? Well, now you have the building blocks to figure it out. The shell has to fork twice, and then in that critical moment before calling exec, it has to cleverly rewire the connections between them. It's all just a more complex dance using the same simple, elegant steps we've talked about today.